Hello and welcome to the first video of the FP1 chapter Coordinate Systems. Starter on the screen to get you going. If you've got time, give this a go. Combine these two equations to eliminate the variable x. So if we rearrange this, we can write this as x equals 5 minus yz, and then we can substitute that into here to make y is equal to 4 times x squared to become 5 minus yz all squared plus z. So we rearrange one of them and then substitute that into the other equation to eliminate the variable we don't want. And this is an idea that we'll come back to later in this video. So this is the first video of coordinate systems, just introducing you to the idea of parametric equations. We'll talk about how to plot them and how to convert from parametric equations into Cartesian equations. Then in the rest of the chapter we'll focus on two particular types of curves, parabolas and rectangular hyperbolas. We'll look at some stuff with parabolas here with an additional example, and then for this one we'll focus on tangents and normals and a couple of additional examples there. The reason I've put these as separate sections is because they come with their own exercises in the textbook. So here we go with parametric equations. Parametric equations are a way to express the x and y variable independently, so they don't depend on each other. Usually we have y as a function of x, but in this case we're going to have x and y as a function of a parameter t. So usually we have, let me write an example, usually we have something like this, where y is defined as some function of x. You choose an x value, you put it in, and you find the corresponding y value. For parametric form, we have two different things, something like this. That tells you your y coordinate in terms of t, and then you have probably a different function to tell you your x coordinate, but still in terms of t. So this t, when you choose a value for t, you put the same value in this equation, and that tells you the coordinates x and y for that t value. So that's the basic idea. You might immediately ask the question, why? And that's a good question to ask. One reason is because on certain graphs this helps us to identify unique points. If you've got a graph like this, which is the sort of graph we'll look at in a minute, if you look at any given x value, let's say x equals 5, usually that's how we identify a point. But in this case, there are two values of y that correspond to that x value, and we could be talking about this point, or we could be talking about this point. However, for the parameter t, every point on this curve has a unique t value. So we can identify if it's this point or this point, instead of using the x coordinate, by using the parameter t. Now you could argue, why don't we just use the y coordinate? That's not really a big deal, it's just a matter of convenience. A better reason is that there are some curves that are just very, very difficult to write in Cartesian form and are much easier to write in parametric form. A good example is something like this, where you can see this would be a difficult thing to write in Cartesian form because it's not a function in a strict sense. Having two equations, one for each coordinate, can make it a bit difficult to know how to sketch the graph, though. It's not always obvious how they will interact, so when you come to plotting or even sketching parametric equations, create a table of values to help you. Just as you have been doing for years to plot graphs, this is a very good way of sketching parametric equations. So whatever your x coordinate function is, put that there, and your y coordinate function can go there, and then you literally just fill out the table and use that to help you do a sketch. I'm sure you can do that, so I won't go through this example, but I'll do the one on the next screen here. Sketch the curve given by the parametric equations, this and this, where t is a real number and where a is a positive constant. This one is a little bit more unusual because we have this a in here, so everything that we do will have to be in terms of a, including the scale on the x and y axis on our graph. And there's a reason that that a is there. We'll come back to that in a later video. So we bring up our table and you choose some values for t. Usually this string of values is quite convenient because you're quite likely to go through the origin here. So in our x box we've got x is equal to at squared and y is equal to 2at, and then we go ahead and fill in the table. So when t is minus 3, here we've got a 9a and a 4a, 1a, 0, 4a and 9a, and then the y coordinate minus 6a, minus 4a, minus 2a, 0, 2a, 4a and 6a. So sketching our graph, we're going to need 2, 4, 6a on the y-axis, and the same on the negative. And then on the x-axis, we're going to need to get up to about 10, so 2, 4, 6, 8, 10. And then we go ahead and sketch our points. So we have 9a minus 6a, that's down here somewhere, 4a minus 4a, a minus 2a, 0, 0, a 2a, 4a, 4a, and 9a, 6a. So I hope you can see that I can't call this a plot of the curve because it is not accurate. But I have done it slightly more accurately than I would normally do a sketch, because looking at these equations like this, it would be difficult to know exactly how it looked. So by calculating the coordinates of a few points and sketching them out a little bit more accurately than usual, I can be quite confident that the graph looks something like this. And I don't need to be too worried about getting it perfect because it is just a sketch. And you can see it kind of looks like a y equals x squared curve on its side, and that's not a coincidence. We will come back to that in a moment. So the second thing in this video is to convert from parametric equations to a Cartesian equation. Because often you can do this, although you cannot always do it. So to do this, we need to combine the two equations to eliminate the parameter t. So we're putting the two equations together to get rid of t and have one equation with y and x, as we normally have. And sometimes this is quite straightforward, it's quite easy. You just rearrange and substitute like simultaneous equations, like we had in the starter question. But sometimes it can be more difficult, sometimes it can be much more difficult, and sometimes it just isn't possible. So we'll keep with the same parametric equations because of the type of curve that this is. It comes back later in the chapter. So we still have x equals at squared, y equals 2at, and the sketch that we had from the previous example is a sketch of this curve. T is still a real number, a is still a positive constant, and we need to find the Cartesian equation of the curve. So this example is quite easy, because in order to rearrange and substitute, we can turn t into the subject of this formula quite easily, just by dividing everything by 2a. And then we can substitute this for t in the x equals at squared formula. So if we substitute y over 2a for t, that becomes this. And then we can tidy that up a little bit. We've got ay squared over 4a squared. One of the a's cancels. And that gives us the equation x equals y squared over 4a. And hopefully here you can see why the curve looks like an y equals x squared curve on its side, because it kind of is. We have something that looks like this, and I'm comparing it to something that looks like this. This is y equals x squared. And this is kind of x equals y squared. Except that we've got this 4a down the bottom here. And you might wonder, why is that 4a there? There is a reason for that, which we'll come back to in the next video. So while this helps to explain why the curve looks like this, you're more likely to see it written like this. And this is the Cartesian equation for these two parametric equations. This is the curve with a 4a in front, and the name of this is something that's familiar to you because of this curve. This is called a parabola. And the general equation of a parabola in parametric form is this, and in Cartesian form is this. And this is one of the two main curves in this chapter. The second main curve in the chapter is this one. Parametric equations x equals ct and y equals c over t, where t is still a real number. The c is still a positive constant like the a in the previous one, but here we need to limit t cannot equal 0 because we're dividing by t in the y coordinate. So the question here is the same: find the Cartesian equation of the curve, hence sketch the curve. So this question is allowing for the fact that it's not easy to sketch the curve from here, but instead of doing a table of values, which we could have done, it's implying with this hence that we should find the Cartesian equation first and use that to sketch the curve. So we should recognize this when we've done it. So let's give this a go. Again, it's fairly straightforward because the equations are not too complicated to rearrange. Here we just make t equal x over c, and then we can substitute that into the other equation. Y equals c over t becomes y equals c over x over c, which we can write as c squared over x. This is something I hope you recognize and can sketch. We'll come back to that in just a moment, but to let you know, this is more commonly written in this chapter as xy equals c squared, where c is still a positive constant. So this one here is a 1 over x graph. It's a reciprocal. So hopefully you know the shape of that from previous work is something like this, with an asymptote on the y-axis and an asymptote on the x-axis. And the asymptotes are there because you can't divide by 0 here, and if you bring this up on the other side and bring the y down, you can't divide by 0 there either, which relates to this t not equal 0. So this is the second curve in this chapter that is used over and over again. We had parabola on the previous page. This one is called a rectangular hyperbola. So we'll be using these two curves a lot in the following two videos. But for now, that should be enough for you to sketch some parametric equations of different types by drawing a table of values, and combine parametric equations of different types to form Cartesian equations, and you can do this using the questions from exercise 4a. We'll come back to parabolas in the next video and rectangular hyperbolas in the video after. Maybe I'll see you there.